All right, guys, now let's start the next chapter. Chapter 3, Systems of ODEs. So far we were dealing with one independent variable, which we called it X or T, and then also one dependent variable, which we call it Y or X, and one equation that relates derivatives of Y with Y itself and with X, and the goal was to find the function Y. This is a case that we're dealing with it so far. So far, we had one independent variable, X, one dependent variable, Y, and we also had one equation relating Y with its derivatives and with X, say f of X and Y prime to Y nth derivative equal to 0. And the goal was to find Y. Now, how about if I still keep one independent variable, which I can call the X or T, but now what about if I increase the number of dependent variables? So now we want to consider the case where we have one independent variable. Let's call it X again. And one dependent variable, potentially more than one dependent variable. So one or more dependent variables. So this time let's call them Y1 to Yn or Ym, let's say. We have more than one dependent variable this time. And let's assume we have a connection. We know the connection between these variables, these dependent variables, and also the connection with X, and also the connection with their derivatives. So suppose that we have, let's say, M equations relating these functions Y1 to Ym with their derivatives and with X. Let's say if we have M equations of which form, let's say F1 of X and Y1 to Ym and Y1 prime to Ym prime, and let's say Y1 nth derivative to Ym nth derivative equals 0. So this is one equation that relates Y1 to Ym, the unknown functions with their derivatives, and also their relation with X. So such an equation, I can write it in the form F1 of a function of these variables, X, Y1 to Ym, Y1 prime to Ym prime, and all the way to Y1 nth derivative to Ym nth derivative equals 0. And similarly, let's say f2 of x and y1 to ym, y1 prime to ym prime, and y1 nth derivative to ym nth derivative equals 0. And let's say fm of x and y1 to ym and y1 prime to ym prime, y1 nth derivative to ym nth derivative equals 0. So here we have m equations with m unknown functions. These y1 to ym are unknown functions. So here y1 to ym are unknown functions. And the goal is to find these unknown functions. Okay, so if I want to summarize, we still have a situation similar to before, but instead of having one unknown function y and one differential equation, here we have m differential equations with m unknown functions. And in each of these differential equations, we have a relation between these unknown functions y1 to ym with their derivatives and the relation with x as well. So each of these equations can be considered as an equation that gives us a relation between the unknown functions and their derivatives and x. For example, x times first unknown function plus second unknown function plus derivative of third, for example, unknown function equals 0. Or let's say x, or for example, first unknown function divided by x plus second unknown function equals e to the x. Could be anything. So because it could be anything, I wrote the general form as, let's say, f1 of these functions equals 0, or f2 of these functions equals 0, and so on. So let's look at an example. Let's say, consider two unknown functions. Let's say y1 and y2 with two equations. Let's say, for example, x times y1 plus y2 prime plus 3y2 equals e to the x. And let's say y1 double prime minus y1 minus y2 prime equals x over x squared plus 1. So here, if you're wondering, so we have two unknown functions, y1 and y2 with two equations. If you're wondering what f1 and f2 are in this case, well, you only need to take everything to one side and leave and make the right-hand side equals 0. Because if you, in this notation, if you want to define f1 and f2, you just need to take everything to one side. So for example, for the first equation, if I take e to the x, the left-hand side, then x times y1 plus y2 prime plus 3y2 minus e to the x. This whole package will be my f1 of x and y1 and y2 and y1 prime and y2 prime, because we have all the way to say first derivative. And similarly, if I take this one to the other side, y1 double prime minus y1 minus y2 prime minus this function will be f2 of x and y1 and y2 and y1 prime, y2 prime, y1 double prime, y2 double prime. Normally in the question, it's not asked from you to find FIs, but I can also mention it if you're just wondering what FIs are here. So here F1 of X and Y1, Y2, Y1 prime, Y2 prime is XY1 minus plus Y2 prime plus 3Y2 minus e to the X. And F2 of X and Y1, Y2, Y1 prime, Y2 prime, Y1 double prime, Y2 double prime is Y1 double prime minus Y1 minus Y2 prime minus X over X squared plus 1. And then we have F1 equals 0 and F2 equals 0. We can write our equations in the form of F1 equals 0 and F2 equals 0. So let's look at an example. Suppose that we attach two objects. With two objects with masses M1 and M2 to a spring with constant K. So we have a spring with constant K here, and we attach two objects, one with mass M1 and one with mass M2. And each of these masses will have their own displacement function. Remember in the previous chapter, we were trying to find the displacement function when we attach an object to a spring. So here we are attaching two objects to our spring, one from right-hand side and one from left-hand side. So each of these mass objects will have their own displacement function. So I'm denoting those displacement functions with x1 and x2. In previous chapter, we used the notation u1 and u2. Here we are using the notation x1 and x2. So x1 of t is basically the displacement function for the first object. And x2 of t is the displacement function for the second object. And how can I determine x1 and x2? Well, we just need to use the Newton's law. We know that m for each object, ma for that object is the total force, and the total force can be computed with Hooke's law. So here x1 and x2 satisfy the following system of ODEs. So basically M1 X1 double prime, which is M1 A1. Like by Newton's law, we know that MA is equal to the total force. And what is the total force? Total force can be written as K times the displacement. Displacement will be X2 minus X1. So by Hooke's law, the force can be written as K times X2 minus X1. Now, why is this the case? Well, see if X1 and X2, both of them are equal. Let's say if X1, the first object, moves 5 centimeters towards right and X2 moves 5 centimeters towards right, then there's no stretch or compression in the spring, and therefore no force will be applied to any of the objects. So in that case, if x1 is equal to x2, the force will be 0. And if x1 is bigger, let's say x1 moves 5 centimeters towards right, x2 only 2 centimeters. So then it's like, overall, it's like that the first object moves 3 centimeters. Basically, the spring is stretched by 3 centimeters. And it will apply a force towards left, because if this is 5 cent, like overall 3 centimeter, and then the spring will apply the force to the objects towards left, which is our negative direction. So if x1 is bigger, then the force will be negative. And how much, what negative number? The difference between x2 and x1. Like if x1 is 5 centimeters towards right, x2 2 centimeters, it's like overall 3 centimeter, and it will be negative. So if x1 is bigger, then the force will be negative. And similarly, if x2 is bigger, force will be positive. And how much? By the difference of x1 and x2. So that's why that the force on the right hand side, we wrote it as k times x2 minus x1, which will be 0 if x1 and x2 are equal, because there will be no stretch. If x1 is bigger, there will be a negative number by the amount of the difference between x1 and x2. And similarly, if x2 is bigger, there will be a positive force. Positive force means towards right direction, and negative force means towards left direction. And if x2 is bigger, we'll have a positive force, which means towards right direction by the amount of x2 minus x1. And similarly, we can write the equation for the second object, m2. x2 double prime equals k times x1 minus x2, which we can also write it as minus k times x2 minus x1. So here we have two. So this is a system of ODEs with two equations. There are two equations. How many unknown functions do we have here? Here are x1 and x2 are displacement functions, which are our unknown functions, with two unknown functions, x1 and x2, and with one independent variable, t. We have one independent variable t and two unknown functions, x1 and x2. So this is an example of a system of ODEs. Practical examples, because in practice we could have a spring with two objects attached to it. Therefore, we'll have two displacement functions, and the goal would be finding those two displacement functions at the same time by solving the system of ODEs, because x1 and x2 they're connected together, and their ODE is also connected. So we have to consider the system and the equations at the same time and solve for x1 and x2 simultaneously. Similar to for algebraic equations, where you have, for example, two equations with two unknowns, and you have to solve them simultaneously, like 2x plus y equals 5, for example, x minus 5 equals 6. So here x and y are connected, and you have two equations with two unknowns that have to be solved simultaneously. So similarly, we have a similar idea for ODEs. This time, instead of two variables we have, or two unknowns, here we have two unknown functions and two ODEs that have to be solved simultaneously. Now let's look at the next example. Consider an equation. Let's say the following ODE. Let's say y third derivative plus 3x squared y second derivative minus 6y prime plus 7y equals 0. We want to rewrite this equation as a first order linear system. So here it's a third order differential equation. We want to reduce it to first order. If we can reduce it to first order, that would be a great news, because we solving first order equations were very easy. We will see that even solving first order systems is straightforward. And that's a great news. Instead of solving a third order equation, we can solve a first order system. So we can reduce the order basically. So the idea here is, if you want to, so right now we have one equation, but third order, we want to have few equations. Instead of one equation, we can have 2 or 3 equations. That's okay, but each of them must be first order. So we want to increase the number of equations, but reduce the order of derivative. Okay, so that's the idea. So the solution, the idea is to set, or let's say to define, let's say 3 unknown functions let's say y1, y2, y3 as follows. As a y1, I want to define it as y itself. y2, I want to define it as y prime. And y3, let's define it as y double prime. Then when I look at this equation here, how can I rewrite it? Because here the equation is about y third derivative. So let me write this equation one more time. Equation above says that y third derivative is equal to a minus, if I take the other terms to the other side, I'll have minus 3x squared y double prime plus 6y prime minus 7y. Now, y third derivative can be written as y3 prime, because y3 is defined as y double prime. So y third derivative is same as y3 prime. So y3 prime is equal to minus 3x squared y double prime. That y double prime is same as y3 plus 6y prime. Y prime is same as y2, and minus 7y, y same as y1, minus 7y1. So we can say that the equation above can be written as, or is equivalent with the following system. So the equation, the third order ODE above can be reduced to a first order linear system as follows. So y2, we are defining y2 as y1 prime, or let me write y1 prime is equal to y2, because y2 is, we are defining as y prime, but y itself is same as y1. So we can say that y1 prime is same as y2. What about a y2 prime? y2 prime will be y double prime, which is same as y3. See, this is y2, so y2 prime will be y double prime. And y double prime, look at here, y double prime is same as y3. So y2 prime equals y3. And what about y3 prime? Y3 prime, we just found it here, minus 3x squared y3 plus 6y2 minus 7y1. So here, see, we have three equations. Instead of one equation, we have three equations. So we increased the number of equations. So basically, we reduce the order of the equation in the cost of increasing the number of equations. We increase the number of equations, but we reduce the order. The highest derivative that you can see here is 1. So we have a first order system. It's not an equation, it's a system because there are three equations, but it's first order because the highest derivative appeared in any of them is first derivative. So in this type of question, this is the idea. So y1, we define it as y. So we started with the original unknown function y. We defined y1 as that function, y2 as derivative of that function, y3 as second derivative of that function, and so on. Here, the third derivative was involved, so we just needed to continue until y3. And then the third derivative can be written as derivative of y3. So this equation here, we replace this one as derivative of y3. We are okay with the derivative of any of these functions because we want to have first order system. So we are okay with the first derivative of any of these unknown functions. We just don't want to go higher than first order derivative. So it's okay to have y3 prime because it's okay to have first derivatives involved or appeared. And then the right-hand side, we had each of these functions, y double prime, we knew that it was y3, y prime, we knew y2, y, we knew it's y1. So we got this equation, which is my third equation here. And what about the first two? See, the first equation here, there is no derivative involved or appeared. So I'm not writing it in my system because I want to write equations where the first derivatives appear. But the second equation here, y prime, basically I combine the first two together because it says y prime equals y2, but y, it's equal to y1 from the first equation. So I wrote the first two equations combined together. I wrote them as y1 prime equals y2. And then the third equation here is the second equation is same as second equation appeared here. How? Because, well, left-hand side is y3. And we said that y3 equals y2 prime. y3 equals y double prime here. But we just mentioned that y double prime is same as y2 prime because y2 prime will be y double prime if you just differentiate both sides of this equation. So basically, if I want to summarize, see the third equation is derived the way that I explained that, y third derivative can be written as derivative of y3. And then we took other terms to the other side. We wrote them as y1, y2, y3. And for the first two equations, how did we find them? I combined the first two equations here to derive the first equation here. And I combined second and third equations here to write the second equation here. And I also explained about the third equation. So we had a third order ODE, which we could write it as three equations and each of them first order. So this is called first order system of ODE, and it's a linear system of ODE because each of these equations are linear. If you look at each of these equations, there is no power. The only power that appears is for x, which we are allowed to have a power of x. even for a linear ODE. But we are not allowed to have powers of unknown functions. So here y1 or y2 or y1 prime or y2 prime, none of these functions have any powers here. So for this reason, each of these equations are linear because no powers of y1, y2, or y1 prime, y2 prime are appeared. Each of them are linear, and therefore this system is called linear system. So note, each of equations above are linear. So here we have a linear system. So equation above is linear. And highest derivative appeared is first derivative. So we have a first order linear system. All right. Now let me give you an exercise. So similarly, you can guess that if you have a fourth order the ODE, we can write it as 4 equations and each of them first order. So here in previous example, we had the third order ODE. We could write it as 3 equations, each of them first order. And if you have a fourth order ODE, we can write it as 4 equations, each of them first order. So rewrite the equation y fourth derivative minus 3 sine x, y third derivative plus 6y equals x squared as a first order linear system of ODEs. So these examples show that any equation, even third order, fourth order, or any order, can be written as a first order linear system of ODEs. As long as the original ODE is linear, we can write it as a linear first order ODE. So that's why solving first order ODEs is very important, because even if we have a third order or fourth order ODE, we can still write it as a first order system of ODEs. So examples above suggest that any linear ODE from any order can be written as a first order linear system of ODEs. And for this reason, we will focus on solving linear first order ODEs in this chapter. So we will focus on solving linear first order ODEs in this chapter. Because the significance has been already shown. this fact that, any linear ODE can be written as first order linear system, it proves and shows the significance of studying and solving first order linear systems. And for this reason, we will focus on solving first order linear systems in this chapter. Now, again, similar to what we had in the previous chapters, before solving the equations, we first studied uniqueness and existence of solutions. So we want to do the same thing here. So we will start by looking at the uniqueness and existence of solutions. So uniqueness and existence for first order system of ODEs. So consider a first order system of ODEs, a first order system of ODEs of the form, let's say f1 y1 prime, because we are assuming first order, so the highest order derivative will be 1. So let's say y1 prime equals f1 of x and y1 to, let's say, ym. y2 prime equals f2 of x and, let's say, y1 to ym again. And all the way to, let's say, ym prime, fm of x and y1 to ym. So consider a system of this form. So suppose that each of these functions, f1 to fm, are continuous and also suppose that the partial derivatives of these functions respect to y's, yj, let's say dfi to dyj for I cos 1 to m and j cos 1 to m exist, each of the partial derivatives exist and are continuous. Then we can say that the system above with the initial conditions. So how many initial conditions do we need? We have m equations, each of them first order. So in total, we need m initial conditions. With the initial conditions, let's say y1 of x0 equals y10 all the way to ym of x0 equals ym0 for some constants. For some constant x, y10 to ym0. So if the functions are continuous and the partial derivatives exist and are continuous, then this system, along with these initial conditions, has a unique solution. So what is the condition that we need to have in order to be able to guarantee the existence and uniqueness of the solution? Continuity of each of the functions f1 to fn, and existence and continuity of the partial derivatives of each of these functions respect to each of yi's. So let's look at an example. Use theorem above to show that the equation y third derivative plus 3x squared y double prime minus 6y prime plus 7y equals 0 with the initial conditions, let's say y of 1 equals y prime of 1 equals y double prime of 1 equals 3, has a unique solution. See, before this theorem, we were not able to prove existence and uniqueness of the solution for this type of equation, because in the first chapter, we only learned the existence and uniqueness condition for first order ODEs. Here we have a third order ODE. But because the technique that we just learned gives us the opportunity to reduce a third order ODE to a first order system of ODEs, and because we now have a condition, we now have a theorem for existence and uniqueness of solution for first order system of ODEs. So therefore now we are able to prove existence and uniqueness of solution for this type of equation, although this equation is third order. So how should we do that? First, we need to reduce it to first order ODE. We already saw how to do first order system of ODEs. We already saw how to do that. And then we can apply the theorem that we just learned, that if we have a first order system of ODEs, like y1 prime equals some function all the way to yn prime equals some function, as long as those functions are continuous and their derivatives respect to y also continuous, partial derivatives respect to y are yj's are continuous, then we can say that the solution exists and is unique. So we saw the answer is, we saw in above that we can write this third order ODE as a first order system of ODEs. How did we do that? Well, we said that y1 prime will be same as y2, y2 prime will be same as y3, and y3 prime was same as minus 3x squared y3 plus 6y2 minus 7y1 with the initial conditions. Now the initial conditions can be written as conditions can be written as, so what are the initial conditions? The first initial condition says y of 1 equals 3. But what is y? Y was same as y1. Remember? Y, we said Y is same as Y1, Y2 will be same as Y prime, Y3 will be same as Y double prime. So Y of 1 equals 3 can be written as Y1 of 1 equals 3. Note that Y1 is same as Y. And we also mentioned that Y prime of 1 is 3. But what is Y prime? What is Y prime? Look at here. Y prime is same as Y2. You can also see it in here that Y prime is same as Y2. Y double prime is same as Y3. So Y prime of 1 equals 3 can be written as Y2 of 1 equals 3. Again, note that Y prime is same as Y2. And similarly, Y3 of 1 equals 3. Again, note that Y double prime is same as Y3. So here, what are the functions that that are mentioned in the theorem? In the theorem, like some f1, f2, f3 are mentioned. Here m is 3, so f1, f2, f3. What are they here? Well, f1 is the function that is equal to y1 prime. Here y1 prime is same as y2. So f1 is same as y2. Similarly, f2 is same as y3. And f3 is the function appeared in the right-hand side of this equation. So let me call this system, let's say, system 2 star. By comparing two star above with the theorem above, we can say that f1 of x and y1 and y2 and y3 is equal to y2. F2 of x and y1, y2, y3 is equal to y3. And f3 of x and y1, y2, y3 is equal to minus 3x squared y3 plus 6y2 minus 7y1. So these are basically polynomials. Each of these functions are polynomials. Because, see, here we have 4 variables. Let's say if you are familiar with the concept of polynomial, let's say p of x equals an x to power n plus to a1 x plus a0. But let's say, what about if you have a polynomial of 2 variables, let's say x and y? Then we can write this one, let's say some constants, let's say n and m, x to power n, y to power m, and so on, right? So as long as you have integer powers of x and integer powers of y multiplied together times some constant and then added together, you have a function of 2 variables. Similarly, you can define a polynomial of 3 variables and so on. So here I have 4 variables. And here I have, for example, y2 is one of my variables. And what is the power of y2? Power of y2 is 1. And no other powers are appeared. Y3 is one of the variables. Power of it is 1. Here, x is one of the variables, power is 2, y3 power is 1, y2 power is 1, y1 has power 1, and then added together. So this is also a polynomial. So each of these 3 are polynomials. But if I had, for example, let's say e to power y3, e to power y3 would not be a polynomial. Or let's say if I had root y3, again, this would not be a polynomial, because for polynomials, all the powers must be non-negative integers. But when you have root y3, that means power is 1/2. Or if you have e to power y3, again, it's not a polynomial. Or let's say if you have 1 over y3, not a polynomial. Sine y2, for example, not a polynomial. If you have things like that, then you don't have polynomial. But right now, every fi that we have is a polynomial. So each of them, so these are basically polynomials in four variables, x and y1 and y2 and y3. And we know that polynomials are continuous everywhere. And polynomials have continuous partial derivatives with respect to each of variables. So theorem above guarantees that the system above, the linear system above, the first order system above has a unique solution for y equals y1 and y2 and y3. And therefore, the equation also has a unique solution because we know that y is equal to y1. We want to know whether there exists a unique solution for y for this equation. Well, we just proved that there is a unique solution for this system. So that means there is a unique solution for y1, unique solution for y2, and unique solution for y3. So that means because y1 has a unique solution and y1 is equal to y, so that means there exists a unique solution for y for this equation. So there's a unique solution for, let me write it this way, there is a unique solution for y1, y2, y3. Now, since y is equal same as y1, we can say that, can conclude that the ODE that was given to us originally, which was this equation, has a unique solution for y. Can conclude that y double prime, y third derivative plus 3x squared y double prime minus 6y prime plus 7y equals 0, with y of 1 equals y prime of 1 equals y double prime of 1 equals 3, has a unique solution for y. All right, so to summarize, the idea was to write this third order system, this third order equation as a first order system. This was our first order system here. And initial conditions could be written in this form. Now, the theorem said that as long as you have a first order system, look at the functions on the right-hand side. If these functions are continuous with continuous partial derivatives, which is the case here because each of them are polynomials, and polynomials are continuous with continuous partial derivatives. And if you have a system with fi's being continuous with continuous partial derivatives and with m initial conditions, here we have three equations, so we need three initial conditions of this form, then we can guarantee existence and uniqueness of solution, for each of unknown functions. Here we have three unknown functions, y1, y2, y3. So we can guarantee existence and uniqueness of solutions for y1, y2, y3. But we know that y1 is same as y because this is how we define y1. We define y1 as y. So if there is a unique solution for y1, and we know that this equation is equivalent with the system that we just saw above, and we know that y is equal to y1, so that means this equation has a unique solution for y. And this is what we were trying to prove, that this equation, along with these initial conditions, has a unique solution for y. Okay, guys, that's all for today. So thank you and see you next time.